Hello everybody. Here we talk about the quadratic parent function. It looks like that. Y equals x squared, or we can write it as f of x equals x squared. This is the parent function to all quadratics that are functions that their highest power is a square. For example, this one is such a quadratic, 2x squared minus 5, or it could be 5x minus 3 squared plus 1. All of those are quadratics. Another one could be this one, 3x squared minus 3x plus 2. You see that the highest power is a square, and also there could be a first power, x to the first power, but there is no x cubed or x to the fourth or any of that things, and of course not 1 over x, 1 over x squared. Those don't count. But if the highest power was x cubed, that would be a cubic function that would be generated by the cubic parent function. So here we are talking about cases that look kind of like that. Okay. Now, why is the parent function useful? It is useful because if we know the parent function in its graph, we can transform it and graph any quadratic in the universe. Alright, how do we find out what the parent function's graph is? We start by a chart. That would be the parent chart. It has x on one column and it has y on the other column, and usually we put the rule, which is x squared, and so we remind ourselves what we are dealing with. To do the chart, you need to plug in some inputs and find the outputs and get points that you plot, then you get the graph. The first simplest point is 0. Are we allowed to plug in 0? Yes, we are allowed here. We wouldn't be allowed if we had 1 over x as the rule of the function, because plugging in 0 would give us 1 over 0, which is basically infinity, and we're not allowed to have infinity as a number, therefore we're not allowed to have 0 in the denominator. That would be something that we often call as undefined. So here we're allowed to put a 0. So what do we put on this column? Well, let's see. If we plugged in x, the rule is that take the square of it, and that's going to give you the output. So if the input is x, square it, and then you get the output. Here the input is 0. I'm going to square it, and that's going to give me the output. Now this is the condensed form. I have to expand it to see what it really is. That's 0 times 0, which is 0. Okay, so when the input is 0, meaning when x is 0, the output is also 0, and I get the point 0, 0. Okay, now let's plot that point. It's right there at the origin. Is that enough to help me do the graph of the parent function? No, because by one point I can't define a curve or a line or anything. The curve could be like this, like that, could be a curve like this or like that, or anything really, as long as it goes through that point. It doesn't narrow it down enough, so I'm going to use another point. I use 0 as the input, the closest whole number close to 0, and positive is 1, so I'm going to plug in 1 under x. Under y I'm going to put 1 squared. That's the rule. Whatever you put for x, you square it, and that's the y. So 1 squared, let's expand it. It's 1 times 1, which is 1. That gives me the point 1, 1. Now I'm thinking, let's see, is that enough? Let's plot it. If I plot it, I'll see that it goes right there. And well, if the graph was a line, 2 points would be enough. But maybe the graph is a curve that goes like this or like that, or maybe it is a wave or anything at all. I don't know what it is. So I'm gonna try to specify. I'm gonna add one more input, and I'm gonna try to stay close to 0. I put 0. So here I put 0. Here is 1. I'm gonna put another. The negative 1, which is also close to 0. And let's see what happens. So negative 1. Now here there's a big common mistake. A lot of the students will write it like that, negative 1 squared, and that would be a mistake. The correct expression would be negative 1 in a parenthesis squared. So let's see why. Let's see the difference between negative 1 squared and negative 1 in parenthesis squared. The difference is that without the parenthesis, the square only sees the 1. So when it gets expanded, it expands the 1. And we get negative 1 times 1. Now negative remains. Now 1 times 1 is 1. So the answer here in this case would be negative 1. In this case though, let's see what happens. The square sees the negative and the 1. The entire thing is the base. And when I expand it, I get negative 1 times negative 1. Negative times the negative is a positive. I don't write it. Negative 1 times 1 is 1. So you see those two are different. One is positive, one is negative. The correct, in my case, depending on the case, maybe this would be the correct one, but in my case, when I plug in a negative number, I always put it in a parenthesis, and if I expand it, I'll see that the answer is 1. Negative times a negative is positive, 1 times 1 is 1, so that would be the answer. Don't make this common mistake. Always plug in a negative number inside the parenthesis. Now what's the point here? X is negative 1, Y is 1. Okay, so I have another point. That point is right there. Immediately I see that it's not a line. But what could it be? Could it be a V? Could it be a U? Could it be a wave? Let's find out. I need more information. So I'm gonna stay close to 0, but now I'm gonna go to the right a little bit. So the next input would be 2. What's the output? Well, it's gonna be 2 squared. Expanded is 2 times 2, which is 4. That gives me the point 2, 4. And usually when we plug in a number, we put its opposite. So let's just put the opposite of this number and see what happens. Again, I'm going to plug it in inside the parenthesis, squared. That's going to be negative 2 times negative 2. Negative times a negative positive, 2 times 2, 4. And what I get here is the negative 2, 4. Okay, let's plot those points. This point, the 2, 4, is right there. And this other point, the negative 2, 4, is right there. So that here is the 2, negative 2, and the 4. Before I continue, I see something. No matter if I plug in negative 1 or positive 1, the output is 1, meaning positive. Also, no matter if I plug in 2 or negative 2, the output is 4, which is the same and positive. That happens because the square is going to kill any negative number you're going to plug in. And this repetition here, 1, 1, 4, 4, is indicative to some symmetry that describes this function. Alright, so I have those points. Immediately I see that my question, was it a V or was it a U? It is answered, it's not a V, it's not a wave, looks like it is a U. Alright, let's draw that U as much as we can, as well as we can. and it's going to be curved at the bottom, and it's going to let's try again. It's going to be a little curve, not too pointy at the bottom, and it expands like that. I don't like this. Let's try again. That is good enough. It keeps going forever up and expands left and right. Now this is the graph of the y equals x squared. We always write with the same color the name of the function which graph we're dealing with. Now this has a name. The most common name is a U-shaped curve. It has also the official math name that is called a parabola. Every time anything falls freely, like when you throw a rock and that rock keeps going, it does a path before it hits the ground, it does a parabola. So this is an extremely useful and with a lot of application function and curve. Okay, so that is the graph of the quadratic parent function. Now there are some attributes that I want to study and know. The first is the y-intercept. That's the y-coordinate of the point that the curve intersects with the y-axis. It's this point here. We see that the y-coordinate is 0. Now the x-intercept, it's the x-coordinate of the point where the graph intersects or crosses the x-axis. We see it's this point, only it doesn't cross the x-axis. It touches it. It still counts, so it's still 0. Then we have the domain. The domain usually it's in that format. Some number less than x, less than a number here. So let's see what we put in those positions, and if it's less than or equal to. To find the domain, to find the domain, we need to remind ourselves that the domain is related to the x-axis. The domain is the set of all inputs. This is, in a sense, this is our domain, where we come from, where the inputs come from. They are all the inputs. The inputs are on the x-axis. To find all the x, to find the domain, therefore you need to find all the x-coordinates. To find the x-coordinates, you start projecting on the x-axis, and you keep going forever and ever, and you cover all of that. Now you project 0, and then you keep going on the other direction, keeps going forever and ever, and eventually you're going to cover the entire axis. So the domain, the graph of the domain, is the entire x-axis. Okay, how do we write this? Since the domain is the entire axis, all the inputs or all the x that are in the domain are going to be between negative infinity and positive infinity. That's one way to write it. But because and also you don't put equal, because we can never reach infinity. Infinity is a concept that tells you keep going forever in this direction and never stop. Infinity is not a number, therefore we can never reach it because we never stop. We just keep going. Another way to write this is, because between negative infinity and infinity are all real numbers, you can write it like that. Domain is all real numbers. This is the symbol for all real numbers. Make sure you put a double line, otherwise it doesn't mean all real numbers. The next one is the range. Now the range is going to have a similar format. The braces indicate that this is a set, the set of all outputs. It's going to be something or a number less than y, less than something that could be infinity or a number, And these symbols, these inequalities, could also be equal depending on the case. So we're going to leave it like that. The question is, what do we put here and what do we put here? We have to go back to our graph and remember that the range is not related to the x-axis. The range is related to the y-axis. The range is the set of our outputs, and the outputs are on the y-axis. The way to remember is domain is where you come from, which is your inputs, and range is what you try to reach, which is the outputs. So how do we find the range? All the outputs, that's all the y coordinates. Okay, let's project. To find all the y coordinates, we project on the y-axis, and we go like that, and we see that we keep going forever. Now we start from the bottom point that projects at 0, the same thing on the other from all directions, and we keep going. When I say all directions, I mean left and right. There are two branches, so I have to project from the left and from the right on the y-axis. And eventually I see that I cover the entire top y-axis, including 0. Now, how do I write this in the format that I have for the domain? I noticed that the lowest point is 0, which is included because 0 has something to project on 0. It crosses 0, it goes up. So the lowest point is 0, not negative infinity. Oops. Okay, so here I'm going to put 0, and it's going to go up forever, which is infinity. But because 0 is included, something was projected on 0. 0 is the y-coordinate of that point. I have to include it, so I'm going to put equal. So this is the range. Next, I'm going to check something that I saw when I did the exponential functions. I saw there were asymptotes. So let's see if there is an asymptote here. Well, an asymptote means something like that. The function tries to reach the ground, keeps going closer and closer. It never reaches, and eventually it just tries to align with the ground, and the ground will be considered as the asymptote. There could be a case that I had a vertical asymptote. Then it would happen something like that. Here is the vertical asymptote, or maybe the y is the vertical asymptote. Let's just say it's this one, and it will try to align to this and go closer and closer. Here we don't have a horizontal asymptote and we don't have a vertical asymptote. There is no asymptote. Our parabola, it does not try to align to any line at all. Okay, there is nothing to restrict it. So is there any asymptote? There is none. No vertical and no horizontal, no nothing. Okay, there is another new concept though. It's this point over here. That point over here is called a vertex. That point is in a sense the turning point of the parabola. On one side, for example, it goes down, it reaches that point and turns back up. It's the peak of the parabola. And what are the coordinates of it? The coordinates are 0, 0. It's the origin. That happens for the parent quadratic. Other quadratics, transformed quadratics, don't necessarily have the origin as their vertex, but they all have a vertex. And there's one more thing. It's the axis of symmetry. Let's look at this parabola. You see it has two branches, one on the right and one on the left. Now if I fold this parabola about the y-axis, I'll see that one branch is going to fall on top of the other. Another way to see it, if you put a mirror in the middle, the reflection of one branch, let's say the right branch, is the left branch and vice versa. That tells me that there is some symmetry. There is some symmetry about the y-axis, and therefore y-axis is going to be called the axis of symmetry. So the axis of symmetry is a line, and in particular it's the y-axis. Now, what is the equation of the y-axis? Let's see, suppose we don't know. Let's take some points on the y-axis. This point has coordinates 0, 4. What about this point? 0, 3. What about this point? 0, 2. 0, 1. What about this one? 0, 0. 0, negative 1. 0, negative 2. And so on. We see that all the points have x coordinate equal to 0. And that is exactly the equation of the y-axis, which is the axis of symmetry. So it's the equation of the axis of symmetry, meaning all the points have x coordinate equal to 0. How do we write this? We write this like that: x equals 0. That is a vertical line that is the axis of symmetry, and it's exactly on top of the y-axis. It coincides with the y-axis. Okay, and those are the attributes of this graph. The new attributes is the vertex and the axis of symmetry. Now, one thing that I notice is that the vertex and the axis of symmetry, they are related. The vertex goes through, the axis of symmetry goes through the vertex. So maybe I should put some comments here. The axis of symmetry goes through the vertex. That will happen also in the transform functions. For example, let's say we have a transform parabola that looks like that. It will have a vertex. So it will have an axis of symmetry going through that vertex. So when you draw it, make sure that this branch is symmetric to this branch about this axis. Okay, that's a very useful notion. Now, let's look at the vertex. Let's investigate a little bit what happens